Welcome back. In this video, we're going to look at the birth environment of the sun. So many people send a sample of their DNA to DNA ancestry companies in order to learn what part of the world their ancestors came from. And scientists are also interested in ancestry, but they're interested in the ancestry of the sun. Where was the sun born? So how do astronomers sleuth for ancestry? They use what's called chemical tagging. They compare the light spectra from other stars to our sun. And one of the uses of this technique is galactic archaeology. How do dwarf galaxies form, and how and where are they incorporated into the Milky Way? They leave behind streams of stars so they can see which stars were born in the same dwarf galaxy, such as the Fornax dwarf galaxy. So similarly, scientists can compare the sun's spectral signature to that of other stars, and the most similar star is in the M67 cluster, and it's star 1194, and it's actually this star right here. There's about 400 stars left in the M67 cluster. It was born, the whole cluster was formed about 4 billion years ago, which is approximately the same time as the sun. So here's just a comparison of the spectral signature of M67 1194 and the sun. So the sun is in red. This is wavelength on the bottom axis, and this is the intensity on this axis. So you can see that it has almost the same variation in the spectrum of light, and this is just at these wavelengths, so they can look over a much greater span of the spectrum, and they find that the spectra are almost the same. So for example, Liu et al. Stated M67 1194 is also found to have identical chemical composition to the sun, confirming its solar twin nature. And then Mosher looked at M67, and he stated that it passes the chemical and temperature paternity test. And he also stated that it has the correct age. For example, M67 1194 is estimated to be 4.2 billion years old, plus or minus 1.6 billion years, whereas the age of the sun is 4.6 billion years old. So it could have formed in the same cluster from the chemical test and from the age test. So this is just a little video showing the cluster. And they also looked at planets in the cluster because they figured, well, if the sun formed in this cluster, would there be other stars in the cluster that had the same type of planets, the same, wide distribution of planets? And so they looked at M67 1194, and it has what's called a hot Jupiter that's very close to the star, 6.9-day orbital period, which means it's way inside the orbit of Mercury in our solar system. Here it is, artist representation. They also found a few other stars with hot Jupiters. M67 1514 had a hot Jupiter, and M67 S364 also had a hot Jupiter, which was 1.5 times the mass of Jupiter. It had approximately the same orbital time as Mercury. Also, these stars had eccentric orbits. So it doesn't look like M67 was a good place for planets to form. And why is that? Well, the fact that M67 is still together after 4 or 5 billion years is an indication that it was a dense starburst cluster with a lot of gravity that would hold the stars together and wouldn't allow them to, the cluster to break apart and disperse into space. So this cluster originally contained tens of thousands of stars. There's only 400 left now after 4 billion years. But open clusters with fewer stars and less dense stars, they dissipate within a few million years. So, or a few 100 million years. So what is the probability of solar system planets forming in a starburst cluster? Well, Suzanne Falsner analyzed the probability of the destructions of the sun's circumstellar disk in a starburst cluster. And using computer simulations, she determined that the probability of destruction is 100%. And thus the probability of the solar system surviving in a starburst cluster like M67, particularly with 8 planets with nearly circular orbits, much farther out from the sun than, say, a hot Jupiter, would be 0. That's what she concluded. So let's look at the sun's orbit in the galaxy. This is approximately the path of the sun through the galaxy. And M67 has approximately the same path if you look at this top view of the galaxy. But the difference is that M67, it goes about 1,000 light years above and below the galactic plane. So this is a little bit hard to imagine, but what we're looking at is a side view towards the galactic plane. And so M67 goes up and down above and below the galactic plane by about 1,000 light years, whereas the sun only goes up and down by about 250 light years. So what scientists have determined is that it would really be impossible for the sun to go from such a intensely fluctuating orbit to a much less fluctuating orbit without the planets being destroyed, for example. So it couldn't have been naturally thrown out of M67. And Barbara Pichardo et al. Did extensive simulations of this. You know, could the sun have interacted gravitationally with another star and been thrown out of the cluster? And she's found that there's absolutely no possibility that that could have happened and entered Earth's orbit. So the sun is not in a cluster. I think it's right around here. And it's a very sparse place in the galaxy where there's not a lot of other stars. So it's sort of an ideal place for the solar system to form. And it's also at the co-rotation radius, which is another advantage in that it rotates around the center of, or orbits around the center of the galaxy at approximately the same rate as the arms rotate at the sun's distance. So it doesn't cross through the densely packed arms very often. So it's still a mystery in the scientific community as to where the sun formed. They're using this Gaia satellite now to look at, like, I don't know, hundreds of thousands of stars to see if there might be any relationship between the sun and those stars. So far, from a chemical tagging point of view, the best candidate is M67 by far. But it doesn't have the same orbital dynamics that would indicate that the sun formed in it. We'll see you next time.